All right, so this is just going to be kind of going back over what we did yesterday, just with new problems. And in this one, it says the student is curious to know the numbers of cars owned, cars a family owns, is different for teachers at their small private school versus another small private school, school B. Students gather responses from 8 teachers from each school. That's these guys right here. In regards to how many cars does your family have? And so what we're first going to do is find the mean and standard deviation for both of these lists. And the way we do that is the way we've been doing a lot of stuff in this class. We go to Stat, Edit, and you're just going to type in the data. 1, 2, 2, 3, 3, 4, 4, 5, 5. Nope, only 1, 5. And then Stat, calculate 1 bar stat. There's no frequency list or anything like that, so we just go to Calculate. If I go too quickly on the typing in, I'll try and pause a little bit more next time. But our mean is 3. You'll notice we're using mu here, and presumably that's because it's the 8 teachers. It's all 8 teachers at that private school. So they only have 8 teachers at that private school. And then sigma is, again, we're using a parameter here. The population standard deviation is 1.225. And you really do want to get in the habit of recognizing why we're using mu and sigma instead of x bar and s of x. Because these are all the teachers at that school. It's a population. We're now going to do the next thing, which is the other list. So I'm going to clear out this list. You just go to the very top and hit clear. Don't hit delete or you'll lose the list. Like there's list 2. If I hit delete, there's no list 2 anymore. List 2 is gone. So go to the top and hit clear, and then you type these in. So we type them all in, and then we're going to go to Stat, calculate 1 var stat, and here we get an average of 4. So we can see that school B seems to, on average, have another car compared to school A. Standard deviation is pretty similar, though. Oh, no, it's not. It's like almost twice as much. Never mind. So it's 2.12, and we'll say 1. Okay. So it says it appears the families of students at school B, and I think these were supposed to be teachers, right? Yeah, they didn't stay consistent with this. Families of teachers at school B have more cars than those at school A, but how many more on average? And a student wants to know what the mean difference is between the number of cars per family for the 2 schools. They know that they must find each possible difference in the sums, list all those possible differences. And so this is kind of what we did yesterday, because there's not a nice little table there. But we're going to take a random person from A and a random person from B and subtract them over and over again. And so we're just going to find each one. So for example, if we got, actually, are we doing A minus B or B minus A? We're doing B minus A, sorry. So for example, if we got 1 and we subtracted 1, so 1 minus 1, that'd give us 0. If we got 1 and subtracted 2, that'd be negative 1. We're literally going to combine each of these together. So we're going to start off with this guy and subtract each of these, and then we're going to move on to 2 and do the same thing. So 1 minus 2, 1 minus 2, 1 minus 3, 1 minus 3, 1 minus 4, 1 minus 4. This process is not going to ever be necessary again, and it's kind of important to get that across to you. This is a one-time deal, so don't think like this is what this unit's going to be like. So that's assuming the 1 guy was chosen for B, and this is all the differences for A. And then what we're going to do is do 2 minus each of those. So 2 minus 1, 2 minus 2, 2 minus 2, 2 minus 3, 2 minus 3, 2 minus 4, 2 minus 4. Oop, and I forgot the 5, so 2 minus 5, and 1 minus 5. And honestly, since we already did this yesterday, so I'm going to say 1, 0, 0, negative 1, negative 1, negative 2, negative 2, negative 3. Assuming you either were in class yesterday or you watched yesterday, we could spend time doing this for each of these differences. So we could do for 3, 3, 4, 5, and 6, and then 8. We could do these differences for each of those. However, if we typed all those into the calculator, type, we already know what this result's going to be. If you watched the video or you were in class yesterday, mu of b minus a is just going to be the average b, so mu of b minus the average a, which is 4 minus 3, and equals 1. You're welcome to do this if you want to. You can fill in this entire table all the way across, but this is the end result. That's what's going to happen. That's what the average of all of these numbers, 0, -1, -1, -2, -2, -3, -3, 1, 0, 0, 0, and then keep going, keep going, keep going, keep going. That's what the average is going to be, 1, because 4 minus 3. Same thing with standard deviation. Once you type this all in, you could go to 1VAR and it would tell you what the standard deviation is, or you can remember that it's going to be the square root of sigma b squared minus sigma a squared. So the square root of 2.121 squared minus 1.225 squared. And if you want to, I would encourage you to try that, but I promise you it will work out to be this answer. So let's go to this, and second square root, 2.121 squared minus 1.225 squared. 1.731. These are cars. And so the whole point of doing this is to show you really don't have to do it. And so that feels kind of like a waste of time, especially if you watched yesterday's video, because we did the exact same thing when we were talking about that spinner game. If I can find that. Let's see if I have it. No, it's somewhere in here. Yeah. So we did a smaller version of that yesterday with less stuff. So I'm actually kind of curious why we did the smaller one like this with the table, and we made the bigger one be all messed up, but it's okay. So if you paid attention yesterday, here were all the possibilities for the one spinner. Here were all the possibilities for the other spinner. And then in this case, we were finding the addition of those two. So 1 plus 1 is 2, 3, etc. We found the average of those, and it turned out to be 6, which is the exact same thing as just adding these two together. It's the main idea of yesterday. Okay. So it says, what relationship do you notice about the relationship between the individual means and the mean of the differences? So we've hopefully noticed that the mu of b minus a is the same thing as the mu of b minus the mu of a. So that formula we talked about yesterday. As far as the standard deviation, if anyone could actually notice that this is like the right formula, I'd be so impressed. Like I couldn't tell that. I'm just like, we know that's the formula, but there's no way I could have looked at this number and been like, oh, I think if you square both of those standard deviations and subtract them and then square root them, you'll get this. I wouldn't be able to figure that out, but this is the formula. This is a fact. This will always work. Sigma b minus a is equal to the square root of sigma b squared plus, always plus, sigma of a squared. And it says summarize those relationships before with formal rules. I mean, that's what we just wrote right here. So they're very repetitive, and that's okay, I guess. So mu of b minus a is b minus mu of a. Sigma of b minus a, or plus, we can put both right there, is sigma a squared plus sigma b squared. And mu of b plus a, which we didn't look at in this problem, would just be mu of b plus mu of a. These are the main ideas from yesterday and today. All right, let's go to the next page. I'll pause for just a second if you're copying it. But by this point, we've written this like 15 times, so most likely you got it, or you're not going to copy it either way. So then it says, would the difference in means and standard deviation be different if instead of doing b minus a, like we did on the last page, we did a minus b? And so if we do a minus b, hopefully you recognize that switches the order that we're going to have. So then mu of a, just to remind you, on the previous page was 3. Mu of b on the previous page was 4. So this would actually end up being a negative value. The average would be negative. The standard deviation, though, stays the exact same. It's still sigma squared a plus sigma squared b. And so that's going to be, what is that, 1.731. So switching the order does affect, when you're subtracting, it does affect the average, but it wouldn't have anything to do with the standard deviation because it's always plus, you're always adding them together. And so suppose I want to find the sums of all the cars together. I'm going to say that is not something I'm going to do. That does not seem like a good use of our time, because we already know mu of A plus B is simply going to be mu of A plus mu of B, which is 7, 3 plus 4. If you have time and you're willing to kill about 5 minutes of that time, feel free to fill this in, and you can find the average of it, and it will be 7, but I don't think we need to do that. Sigma of A plus B, that formula does not change whether you're adding or subtracting. It's still sigma A squared plus sigma B squared. So this is still 1.731. That is usually what students will mess up, not for the addition. To point out, like, you guys are usually fine with that. It's the subtraction ones that you guys messed up for the standard deviation. You guys put a subtraction sign in there, and that's not correct. It's always plus. And then it says, what do you notice about the relationships? Summarize the relationships with the formula. So I'm just going to skip down. This is very repetitive. Mu of B plus A, mu of B minus A. This formula does not change. It is mu of B plus mu of A, or mu of B minus mu of A, and sigma of A plus or minus B is sigma A squared plus sigma B squared. Absolutely no difference between any of these formulas because it's the same 3 formulas over and over and over again. That's the only thing for today. And then for the rest of the class at this point, all I got is homework day 2. And why don't we do the first problem together just to make sure we're all on the same page. And I think there is a backside to it. It goes up to 7. These should not take more than, I would say, 10 minutes, 15 minutes at the most, if you have the idea down. Ooh, there's some teacher names in here. Mike, Steve, and Phil. Those guys are all upstairs. Okay, so we have Leanne and Suzanne. That's a cool combo. Are competing in a 100-meter running race. And Leanne found out that her mean time during training has been 15.4 seconds with a standard deviation of 1.3 seconds. So those are her mean and standard deviations. Suzanne has found that her mean time during that is 14.9, a little bit faster, but she has a higher standard deviation at 1.8 seconds. And Suzanne expects to win due to her better times during training. If they were to race over and over again, what would be the mean and standard deviation for her winning margins? So we're going to do Suzanne minus Leanne, which is, again, very fun to say. You should try it. You're muted so no one can hear you. Suzanne minus Leanne. So we're going to do the mean of Suzanne minus Leanne, which is just that same formula we've been talking about. Us minus mu L. And so if you, like, this is a pretty good, I feel, conceptual understanding of it. So 14.9 minus 15.4, that's Suzanne's time minus Leanne's. Be aware that you want to have a smaller time. So, I mean, that means she's winning, so just in case we're not clear on that. You can use a calculator, or you can recognize it's going to be negative 0.5. Either way, so that's a negative 0.5. So on average, if they were to do this, if they were to race over and over and over again, like just constantly every day, they just go out there and race again, it seems like Suzanne would typically win by about 0.5 seconds. She'd be about 0.5 seconds faster than Leanne. Hey, Mateo, how's it going? And then we want to find the standard deviation. So S minus L. And that's going to be square root of sigma S plus, always plus. If I had to guess what you're going to mess up on a quiz, that's tomorrow, you're going to forget that that's a plus sign even when you're subtracting here. And then sigma L squared. Very repetitive, like it just is. It's kind of the same stuff over and over again, but I do think that there's some practical applications to this that you might be able to glean from it. So 1.3 squared, use the old calculadora. 1.8 squared plus 1.3 squared gives us 2.22. And so what that's saying, and this is something that Suzanne wants to be aware of, sometimes she's going to lose, because what we've just found out, if you want again, if you want like a conceptual understanding, typically, here's 0. Typically, Suzanne is going to finish about a half second before Leanne. Like she's gonna win by about a half second. However, the standard deviation is pretty wild, so that means that it can happen anywhere in here. So sometimes it's going to be a blowout. She'll be so much faster than Leanne, but also sometimes she's going to lose to Leanne. That's what this range of 2.22 is telling us. So it's plus or minus that 2.22. These are typical values. So again, you don't have to write this on your paper. This is more just to show you like what the heck are we talking about. So 1.72 and then negative 0.5 plus 2.22. Oh, whoops, negative 0.5 minus. So if they just kept racing over and over again, typically Suzanne would win by about a half second, but sometimes she would win by 2.72 seconds, and that wouldn't be atypical. All this is like a range of typical values. But she would also sometimes lose by up to 1.72 seconds. That's the way you would interpret these values. So she is probably going to win. And if you were making bets, if you were looking making bets on these races each day, it probably would be a good idea to bet on Suzanne. However, you need to be aware that sometimes she is going to lose, and that's not going to be surprising when she does. Like on 538, I think during the 2016 election, around election day, there was like 33% chance of a Trump victory, and it's not going one way or the other. I'm not trying to do anything of preference. And 67% was a Clinton. And what people fail to realize, and people are like, oh, statistics was lying and it was all wrong and blah blah blah. This is telling you that if you kept doing these elections over and over again, he wins a third of the time. It's not that surprising. If you were told you have a 1 in 3 shot of getting hit by a car if you go outside, you'd be like, oh, that seems like a pretty serious thing. That's going to happen 1 out of 3 times. I'm not going to go outside today. That just seems like too risky or whatever. So these ranges of values and stats, I think, are really important to understand. I think they give you better understanding of when things that seem surprising happen. You're like, wait, actually that wasn't too surprising. Sometimes Leanne is going to win by up to almost 2 seconds, even if consistently Suzanne wins these by about half a second. Leanne coming in 1.72 seconds faster is not surprising. That's within that range of typical values. All right, so now I'm going to stop this video.